auto stop. All right, restream. Restream thinks we're live. Twitch thinks we're live, and YouTube eventually also thinks we're live. Okie dokie. Well, welcome to Code Hangout number 195. Today is a bit of a started late, didn't think of a topic in time. So there's something I've been working on a couple of days ago. I need to set up a backup server, or at least a second version of the server for SudokuPad. So maybe I can do this on stream, and maybe it won't work. Then we'll have to think of something else to do, because if there's also all sorts of authentication that I have to do, then it won't really work. But basically, I started setting up an image of the existing server. So in theory, I should be able to instantiate that one now. But where's the browser tabs where I had the notes on how to do that? How to... Nope. Because maybe they got shuffled about. Nope. Alright, I'll probably close it. Alright. How to clone an AWS instance. Boom. So I've got the AMI. So I've done that. Alright, cloning instance, blah blah blah. To clone the instance, go to console, image and templates, create image. Alright. Great image. So obviously the image will be out of date, and I don't know how it'll work with SSH keys and all that stuff. So it might be a little trickier than just starting it up. Yeah, well, how's the SSH? Hey, John Paul Adamovsky, how are you? Good morning. How is the SSH key gonna work? Is it the same one? Can I have two servers with the same public key? Maybe. The new server will have a new instance ID, new private IP address, update the configuration with specific instance ID, IP address, host name of the original instance. If the original instance has a last IP, one just has a new last blah blah blah. Alright, no software licenses. I just want to have a second version of the server running. I don't have CLI set up. Alright. Launch a new instance using the AMI. Let's get this over here. So we have the AMI. It should be this one, which I did 3 days ago. Right name, configure additional settings and the reboot option, yada yada yada. Image created. Create the new, select your newly, yada yada. Here we go. Launch instance from AMI. Now the question is, can I adjust the size of the instance? Because I don't want to double my expenditure. Although, I think a lot of my expenditure is bandwidth. So, AWS 4 backup. It's called 4.1. Alright, can I, the T2 micro, can I change this? T2 micro, free tier eligible. It's got 1 vGPU, 1 GB of memory. That might not actually be enough, right? Because I'm pretty sure I have more than 1 GB of memory. Caroline word graph or CWG? Should use the Caroline word graph. What's the Caroline? What are you talking about? What is the Caroline word graph? Recently improved graph. Keep. In respect to what? Hash function for the. Okay. How does that give me a backup server? I'm slightly confused here. All right. So if I do this, I have. Okay, so this one has 8 GB of memory, so this definitely is a bigger instance. If I look at my existing instances, it should give me... it's a T2 large. All right, so this would be a T2 micro. I think I want to have at least 2 GB of memory. I don't think I think the data... Yeah, I might not... Might actually have to go for medium, even. Base price... So this is currently a T2 large. And it is, according to this, a T2 large. It's got 8 gigs, so that's basically the cheapest thing with 8 gigs of memory. Okay. And that currently costs on-demand Windows base pricing, on-demand Ubuntu Linux base pricing. So $9.09 per hour. This one would be half that. So it's pretty much half that. I'd like to look up my billing, but I probably I don't know if I should do that on stream. I don't know if there's nothing weird going on, then I'll put it back on stream. Logos or material determinism. I think you've lost me a little bit here. All right, so can I get... So Amazon Elastic Compute Cloud. Secretive about this. Can I? So in January, I don't know if this is bandwidth or if this is the instance itself. So I don't have a savings plan for this one, so it might be more expensive. I don't even know what this is for. I don't remember setting anything up with this. C2 other. That's also not very useful. Can we get a breakdown? Problem is, I don't know if I can run this stuff with 2 gigabytes of memory. Saving plans for compute usage. So this is compute. This is not the bandwidth. I don't think bandwidth is actually on here. I don't think I exceed free bandwidth. Yeah, I see. I'm actually getting credit for data transfer. Now the problem is I don't remember if the savings plan is for bandwidth or for the instance itself. Credits? Nope. Cost and analysis. I love how it says cost and user analysis and it doesn't really analyze much and doesn't give you any freaking details. Like, that's not really useful. Well, let's just set it up. We can always shut it down again. Jean-Paul, I have no idea what you're on about. Why don't you use that hash function? I don't... A hash function is for hashing. If I'm not hashing something, I don't think I can use a hash function. Alright, but we do need a little bit more memory. So let's go for medium. Okay. Can I... How to keep here not recommended. Can I use this one? Probably. Can I... Security is a set of firewall rules to control the traffic. So I should be able to use the same one. So, what security group are we in? Where is it? Where is it? It's on the networking, I imagine. Or on the security. Okay, so I think it's launch was at 1. Okay. We probably don't need the same amount of storage. Does this give me something on the storage? Do you... Nope. Yeah, it shouldn't be... It shouldn't need nearly as much storage because I'm currently only using... Oh no, I'm using 22 gigabytes. But most of that is logged, I imagine. I think that I think I can but then again, the storage isn't really that expensive. So maybe we'll do 30 gigabytes. Let's see how it goes. We might have to redo this in a later stage. All right, I think that's enough. Do we need to set anything else up? We have a name. Other than that, let's see what happens. As long as it doesn't take the server down. And as long as I can log in. If it doesn't take the server down, we can just shut it down. If I can't log in, well, we can still shut it down. So now the question is this going to show up in here? Oh, wait, did I not tell it where to put it? Is it in a different location? Use East A1. Nope, no, that's the same location. But why does it show that? Oh, there they are. Okay. Is there a filter here? This is 1 of 1. 2. Okay. So now it says initializing. All right. Now it says running. And I have a public IP address. I don't know something that I need to check out because I think this is gonna be a bit annoying. Yeah, I'm gonna look into my SSH config here for a second because I don't remember how this works, and that's part of why I'm doing this. This shouldn't. I hope this is gonna be on the stream. Config. So in my configuration here, I have AWS 4. So if I do config, we should be able to just copy what is there right now for AWS 4. AWS 4.1. Host name. Yeesh, dude. Have you been smoking? All right, so we have a public IP address. Now, it probably won't run without all the different domain names, unfortunately. I'm guessing the user's the same default user. Unless that's changed. Preferred authentication. I am not showing this because I am not smart enough to know if this is a problem. If I were to show it on stream. Forward agent. Yes. And the important thing. So if I now do this and I go AWS 4.1. Ooh. Preferred authentication. Did I misspell that? Authentications. Oh. Should be authentications, not authentication. Okay. Yes. Okay. Now, what I don't know is if it started up all my stuff. And that's part of why I'm doing this, just to see if this will actually work. I'm starting to wonder if my... my stream topic should be updated. Maybe you're mistaking it for the last stream topic, which I'm not working on today. Let me just double check what the stream look. No, it says backup server. That should be it. That should be it. So, John, I'm happy to listen if you give me a clue what you're talking about. All right, so is stuff on here running? Maybe. Okay, so there's some stuff on here, and this is not. I'm not on this one, right? No, that's different. Okay. How can I test it? PM2 logs. Check that. Okay, if I go to the public IP address, I don't think anything will happen. No, but this is definitely my proxy. I need to set up a domain name that points as this thing. And then I need to probably configure certain things. Ah, wait, I can do it with my host file, probably. Right. Is it, where is it? I forget. Drivers, etc, hosts. Right. So if I do something like this is, let's say, alpha.SudokuPad.app, right? And then I open this. No, then I open this. Okay. Now, if I go here and I say, look at the logs for alpha. Okay. If I go here. Okay, so here they don't exist, but on beta they would exist because this image is a couple of, yes. Okay, so that's a pretty good indication that we're looking at the new server. Excellent. Okay, that was, relatively speaking, easier than I thought. So all I really need to do is set up on a subdomain. And then I'll have to configure the proxy and the microservices. Do I need to configure PM2? No, I don't think so. Yeah, I think that's really all there is to it. I probably don't want to do all this configuration stuff on the live stream, so I might have to think of something else to do. What I would love to see now is if these four is I would love to see how much this costs compared to the other one. Because yeah, it gave me the per hour running cost, but obviously there's a bunch of other costs, so I don't know what other costs it accrues, right? But I guess I'll run it for a month and see what happens. Okay. Let me think. Do I want to switch to something else then? I mean, we could go back to looking at puzzle identity, because that's, you know, that is a big subject, and it's definitely far from being done. Ah, wait, let's see if there's anything else. Configure, yada, yada, yada. Review and launch. Automated data, okay, instance configuration scripts. Yeah, well, I don't need to automate it. It's not something I'm going to do a million times. And I'll probably want to figure out a way of cloning the data over. So, for example, well, I can probably do through my local machine. It doesn't have to be perfectly up to date. All right. So, I could do some stuff with the voice. Like, I was looking into a voice synthesis for like reading out puzzle rules and stuff. But I'll probably need to learn a little bit more about that. So let's have another look at what we did the other day, which was puzzle similarity, right? I ran some backups. I did that. All right, that's me working on Piper. Let's have a look at that. So we had the match givens script here, and this one runs from SudokuPad.app from the server. All right. And this one, okay, so what we did last time was, we're switching topics a little bit. We're going back to looking at puzzle similarities. Yeah, so here I was running some sort of offline matching on the givens, right? So I was extracting givens and extracting solutions and so on and so forth. I need a couple of the other steps I need to do is now looking at the other properties, and I need to figure out a sort of infrastructure of how can I how can I easily implement a bunch of different checks, and how can I kind of manage storing, sort of caching certain information offline, such as, you know, checksums and hashes and things like that. And I think there was a research paper I was supposed to look at. I think it's this one. So we're kind of, there is, no, it's not these. These are just the notes. Okay. Same solution grids, solution on the 2x2, 3x3 pattern. Random change. Okay, so these are, we had some notes on, what is that over here? We don't need that anymore. Was it under here? I closed that already. There's some PDF files. All right, well, basically, it was, I think, you know what? I think I downloaded those, so maybe I can just bring them up here. Do this, and let's see if I can find them here. I think there was, oh no, that's this one. It was about matrix multiplication. But this is looking just as a solution grid. I need to figure out the normalized version. All right, let's see if we can just Google that. Sudoku normalization. Because if we can look at solution grids and normalize those, Lucas has been busted. What? Oh, okay. Right, that one is we have, yeah, what is the name of this algorithm? So I don't even know what the naming is, right? We have possible solution morphs. Randomly chosen puzzle, they will be different. Project solutions or randomly chosen puzzle different. Because I'm sure I somewhere have a list of all the Sudoku puzzle solutions. Like somebody built a database, right? John Paul, I feel like you're kind of listening, but not really. I mean, if you know anything about normalizing puzzles, right? So basically all the transformations that make puzzles similar, right? So let's maybe we can derive it from scratch. Maybe that'll be, what are you doing there? Maybe that'll be actually a useful exercise, right? So let's see, Sudoku normal forms, right? Or transforms. I don't know. Basically, I don't know what the word is, but basically transformations that don't fundamentally change the puzzle, right? So, for example, and we're talking about just the classic Sudoku, because here we're just going to compare solution grids. And it doesn't necessarily work for puzzles that have other constraints, but what it gives us a way of finding similar puzzles, right? So we don't care if the puzzle then gets differentiated by another property. You know, we're just looking at one measure here, and then ultimately there will be multiple measures, right? But, for example, we can switch out any of the digits. So I think what the normal form is, and let me bring up some puzzles so we have something to look at. And we're gonna fill it in. Let it be filled in. Nope. Oh, no. No. Enter solution. Here we go. So basically, what it means is we can swap any two, like the digits are just symbols. It's just 9 different symbols. There's no maths involved in a classic Sudoku, right? So it means that we can switch all the 9s with all the 3s, and it's the same puzzle, right? And I don't know if it works by going across the top and starting from 1 and then saying, okay, the digit in the upper left corner is the 1. The digit in the upper, this one will be the 2, so we'll switch the 4 with the 2. This will be the 3, so we'll switch the 5 with the 3. But that's one way of doing it, right? So swap digits, right? So this is one of the transforms. Another transform is, I think we can swap any 2 rows or any 2 columns within the same 3x3 set, right? So this can be switched with this can be switched with this, and this can be switched with this, and this can be switched with this, but we cannot switch this with this, right? Because then we're affecting the box grouping, right? But as long as we're switching these 3, we're not affecting the box grouping, right? So swap row/calls within each 3 within each box grouping. Right. And finally, I think we can switch these 3 rows with any of the other 3 rows, right? So we can switch the box rows and the box columns, right? So in other words, we can switch these 3 boxes with any of the other 3 column boxes, and the same for the rows, right? So and these can go to the bottom 3 or the middle 3, right? So you can swap row call boxes, right? I think that's and then we have 4 rotations, so 90 degrees, 90 degrees, 90 degrees, right? 1 rotation, 2 rotations, 3 rotations. So we have 3 90-degree rotations. And I'm not sure if some of these are like extra. In other words, they can be done through one of the other methods. I'm not sure. Well, probably not by just throwing words at them. Like, the sentences need to make sense. Like, for example, if you say, arithmetic should employ purpose. Okay, that's a statement, but that's not part of a conversation, right? It's not something... If I walk up to you and say, t-shirts should feel soft, you say, okay, maybe. I don't care. What does that have to do with anything, right? It's not part of a conversation we're having. It's just a statement out of the blue with no context. Yeah, but that's basically it. And the final one is flipping it across the diagonals, right? So basically this corner becomes this corner, or this corner becomes this corner. So 2 diagonal flips. Or basically, they don't have to be diagonal flips, right? I think we can flip left to right and top to bottom. 2 flips, right? What I don't know is if we should do the digits first. So basically, we get a 1 in the upper corner. Like, I don't know what the sorting should be, right? So the digits I can sort, 1 through 9, no problem. Okay. But then how do we determine the rows and the columns? Do we sort them by... Like, for example, if I want to look at these 3 columns, if I sort them by the first digits, well, they'll already be 1, 2, 3, right? So I think there's some other calculation. It's sort of like the sum of the first n elements or something. I don't know. Because these would be 1, 2, 3, right? But then maybe these would be different. And then obviously if we're swapping these, then these would get unsorted, right? So the problem is, what's the minimal form? And we have to basically give each of these transforms. Like, I don't mind trying out all the different transforms, right? So we have how many? This is 9 factorial, right? So it's just 9 factorial. Or is it? No, it's not 9 factorial. It's not that many. Because we have 9 options for the first one, 8 for the second. I don't know what you call that. But we'll basically have... So for the first digit, we have 9 choices. 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. 47. All right. That's not factorial. What do you call that? Name for sum of integers smaller than given. I don't know what that's called. But it's called the triangular number. All right, fair enough. All right, so we have 47x swap digits, right? The first box in every puzzle has to be the same for every puzzle. I guess so. I guess that's kind of the index, right? Like you're transforming it until the first box is the same. And the first box should kind of be 1, 2, 3. So I'm guessing the upper left box will always be 1, 2, 3, 4, 5, 6, 7, 8, 9. But the question is, are there other rules for the rest of the digits? Find and just sort them to the lowest possible values as if they were integers, and then you can compare them all. But what would be like an integer, right? What am I sorting? That's what I can't think of right now. So we have 3 times. So we have how many? I don't like thinking of it as swaps. How many options do I have? The first row can have 3 plus 2 plus 1, right? So it's 3 plus 2 plus 1, which is 6 times 3. We have 6 options for each of them, right? So this row A can go, column A can go into 3 positions, column B can go into 2 positions, and column C goes into 1 position, right? So actually we don't have plus 1, because that's always a given. So it's really just 3 plus 2. We only have 5 different ways of doing it, right? Because the last one doesn't give us an option. So we don't actually have 57 ways of doing that. We have 56. So this is 5 times 3. So it's 15x, I think. And let's separate rows and columns. We have 15 times by row and 15 times by column. No, the first box, triangular number. Oh, the whole puzzle board. Ah, fair enough. I suppose. Yeah, okay. Now I understand why why people are looking at efficient algorithms for this, because it might actually be a little problematic, right? All right. Now we have 5 more for rows and 5 more for columns. And it's not 5. We can take one column and put it into one of the 3 places. That's 3 options. And then we have only 2 more options for the other, one way or the other, right? So it's 5 times for row boxes and 5 for column boxes, right? And then the rotations, we have 3. We can have it unrotated. We can have it rotated once, twice, or 3 times. So I guess it's 4 because unrotated counts. Unrotated is one option. Okay, so then no, but these aren't. My brain. I think this is right, and I'm gonna change this to 3x5. All right, the whole puzzle board is an integer, big integer. Yeah, in fact, I might even just use big int. So basically, we want an algorithm that now calculates all these things. And that'll be a fun little thing we can put together in this stream. I don't think that's... And it's something that I should have done a long time ago. Is it permute or permutate? Yeah, permutate. Good enough. Right. So let's grab this one. P81. Right. Let's just do this. Has this become my habit? Pause 1. And now we'll just build a couple of algorithms that lets us do this. Hey, Nodrel, I have a feature request. Clicking outside the grid when using the multi-select clears the selection. It used to work that way. Doesn't anymore. Yes, because somebody had a feature request to change that. So now you just have to click a little longer. Wait a second. Clicking outside the grid when using the multi-select. Yeah. So if I do this, and now you just hold it for like 2-3 seconds. Probably less than 2-3 seconds. 1, 2, yeah. Even less than 2 seconds. Just a long click. Hopefully that's good enough for you. Okay, so let's bring these over. And I'm kind of just doing this for my own satisfaction, because I'm sure somebody's already built a very good algorithm to do this, and I could look them up and all this. But I think going through this myself, step by step, will give me some, you know, familiarity with the ways this stuff works. Also, when did I work on the? I used big ints recently, and it was for. I did a bunch of encoding stuff. Would that be on the Sudoku data? I don't know. I was doing it to figure out compact encodings. It could also be under JS something. Let me see. It's gonna be under here somewhere. Maybe this one. Man, so disorganized. Compression. Sudoku packing maybe. Yeah, big int. Okay, here we go. All right. All right, let's keep it around in case we need to reference it. Okay, so what do we want to do? We want to, well, let's try a couple things, right? We're gonna output +1. We'll probably want to do things like show it as a 9x9 and things like that. Step 2, 9x9. So we're gonna call it P81 to 9x9 equals P81. And it's gonna be P. Let me just refresh my brain. I think if I do this dot match, if I match it against a regular expression, that's 9 digits. And I'll do global. And it'll give me that. And I'll do join like that. Yeah. So if I do this, P81 dot match and join, right. If I permutate, oh, we are not executing this function. Boom. If I do this in main, and then here I'm just going to call wait main. Like if I do this, right. 1, 2, 3, 1, 4, up to 9. So 3, 3, 3. Good enough for now. Okay, so that's a function that lets us output it as a 9x9. Trying to print the transformation of a puzzle solution which does not change the puzzle logic so that the integer produced is set the smallest integer possible. Yeah. All right, so if we now look at the big int of this, I think that's all I need to do, right? Yeah. That's just an n at the end. Should just display the hexadecimal checksum, so a single different digit in a puzzle grid will have an easily visible different checksum. Yeah, it's just until we get deeper into the weeds, right? So I'm gonna do a very sort of primitive implementation of each of these steps completely separately, right? So to permutate something, I've done this before and I don't remember. Trying to remember a good efficient way of keeping track of that in an algorithm without, you know, being able to do it asynchronously. I'm guessing we don't actually care about what digits are which, right? We don't care about them at all. We'll just look at the top 10 digits, right? And we'll just replace them in order with, 1, 2, 3, blah, 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 right? So we want to permutate through these. And we're going to iterate through the permutations. So basically, I want something that lets me count to 47, and each number will give me the permutation, ideally, right? And, if I write them out manually, right, we'll have the first permutation would be this. And the last digits never matters, right? So we'll say we'll pick a 1, then we'll pick a 2, then we'll pick a 3, then we'll pick a 4, yada, 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 all the way to the last digit. And then we'll, because I don't want to have a recursive algorithm, right? So I'm trying to think, how can I get rid of the recursion? I mean, a recursive algorithm would obviously be the easiest. Let me think. So we have 0 options for the last one. We have 2 options. Well, we have 1 option for the last one. 2 options, so it's kind of in reverse, right? So the first digits can be 1 of 9 options. Then 1 of 8, 7, 8. So we got to count through 9, count through 8, count through 7, count through 6, 5, 4, 3, 2, 1, right? Now the problem is, which of these we're getting depends on which ones we've already used, right? So whichever one is the first one here isn't available for the 8, right? So it kind of goes to the end, sort of in reverse, if that makes sense, right? Yeah, recursion is useful, but if we want to, once we want to improve the performance of this algorithm, and we will want to do that, then we'll have to get rid of recursion anyways. And if I figure it out right now, because we'll do the same thing 6 times, right? Hopefully we'll just do it like that, right? So basically what I would like to do is I would like to have a function that takes this number, 0 to 46 and returns one of these iterations, right? And the iteration is basically a list of 9 numbers, right? So basically we want a function that takes 0 and returns, and let's do 0 indexing, 1, 2, 3, 4, 5, 6, 7, 8, right? It takes 1 and it'll return 0, 1, 2, 3, 4, 5, 6, 7, 8, 7, right? 2, and it'll return 0, 1, 2, 3, 4, 5, 7, 6, 8, I guess, right? And it's basically like a binary counter, except, not binary. And in fact, that's the abstraction that I'm trying to figure out. That's 0 and that's 1. Because we'll basically have 9 up front, right? So 0 through 9 is all the ones. So all of the ones, we'll have 8 is the last one with a 0 at the front, right? And no. That's not how it works at all, does it? Okay. So, going from the end, the last position we have 1 option, then we have 2, 3, 4, 5, 6, 7, 8, 9 options, right? My brain. I need a master board. Yeah. Oh man, it's annoying because I've done it so many times, and my brain is not what it used to be. Let's see. Convert recursion to linear. Prepare. Arithmetic notation. Also getting super hungry suddenly, which makes it very hard to concentrate. I mean, I could just write down I could generate all the different orders, right? And in fact, we don't care about what the current digits are. We just care that we catch all the digits that are the same. So there's just an abstract symbol, right? Different comparison to two different of two. Actually, it'll be a comparison of 200,000 different boards because I'm matching the boards against the database, right? And ideally, this is just one of the things we'll match. What I'll do later on is I'll probably also try to do like a one-off match, you know, like get basically a string distance, right? But that's why I want to normalize the boards first. Tempted to just implement I could just implement a recursive algorithm to get me these. So let's just do that quickly instead of just staring and complaining. So calc options, let's call that. So what do we need? We need an array that gives us the actual orders of n elements, right? So we'll start with an n. And we'll do calc options, whatever, right? So if we're calculating one option, do we want to pass in a list of symbols? Probably not. And I think calc options can be called recursively, right? So if n is 0, we don't have any options. So we just say, we're assuming there's only one element, right? So if we're passing in 0, so if n equals 0, return 0. Boom. Right. If we're calculating one option, then we're gonna calculate, we have two values, and each one gets n minus 1 as a possibility, right? Except, is it two values? Because it could be, it'll eventually be more than 2, right? One second. If n is 1, I mean, we know we can hard code it, right? If n is 1, let's just do it this way, right? We want to return 0 and then calc options 1. No, so we do wanna pass in a list of available options. Right. So we have the number of options. Oh, we can just, we can just do this, right? So if we're passing in val 0 and vals 0, 1, now we're caring about the length of vals, right? So now we're saying if vals.length equals 0 or equals 1, then we want to return just vals, right? If it's greater than 1, so else if lost of, well, yeah. Vals length is 1, return vals. Actually, not just 1. Small or equal to 1. Otherwise, we'll take the first element, right? So we'll do vals dot not pop unshift. Or just val 0. Right? No, actually we need to do it once for each item in vals. we need to make we need to make a set. That's kind of how it works, right? So if vowels has two elements, then we need to make two sets. One where the first element is at the beginning and the one where the second element is at the beginning. And then the rest of the set is calc options of the rest of vowel, right? So we need to pull the vowels out of the thing. Yeah, okay. So for each element, for each option in vowels, so for vowel of vowels, right? So that just gives us 2, 0 and 1. And then we will do the rest of vowels. So vowels dot filter v, where v is not equal to vowel, right? And then we'll run calc options on that. So we'll do let rest equal, boom. Right? We'll do rest, and we'll do calc options rest. Now, we want calc options to return an array of options, right? So an array of arrays. So actually this should return that. All right, so calc option 0 returns an array that contains an array with just the element 0. This will return that and that. All right, so we'll want to do this. This would be one of the options, right? So 0's, yeah, so we need to do one of these for each of the elements that comes out of this. So if this returns more than one option, we have more than one result. All right, so we do let res equals array, right? And then or let remainder that, right? We'll have val and remainder itself should be now just a singular array, right? And then these will join like that, and then each of those needs to go onto the results array. Oops. Sorry, I feel like I'm super slow. I haven't done stuff like this in a while. That's kind of why I'm doing it. Get my brain moving again, right? So now we get an array of these two options. Right. Now, if we have 3 options, this happens. If vowels.length is that. Wait, what? So, 1, 2, 3. Yeah, let's get rid of that. So we go straight to 3. So now we're taking the first element and we're calculating the options for that. Right. And then the result is 1, 2, 2, 1 on the first level. Oh, because we're not returning it. All right, return result. And then the final one is 0, 1, 2, 0, 2, 1, 1, 0, 2, 1, 2, 0, 2, 0, 1, 2, 1, 0. And we get 6. 6 iterations. I thought we had 3 for the first. Then we have 2 choices for the second, I thought. For each of the 3. Yeah, and it's 2 times 3. Okay, it's 2 times 3. Okay, no. I was wrong. All right, all right, right. And then if we do this, we should get that many. Right? So the result for vowels so for 0, 1, 2, 3, there's 24. Okay. And we don't actually need to pass in... Well, we do need to pass in vowels here. But we could say if vowels is a number, generate an array, right? So we should be able to say calc options 1. And we'll just say here, if type of vowels equals number, vowels equal, what was it? New array 3, or array 3, set this, dot map underscore I. Yeah. We'll just say array vowels. Boom. So then I should be able to just say something like 3 and 4. Right? And ultimately 9. Okay, so it was 9 factorial. So there are 362,780 different variations. So that's a problem. Because you saw there was a little bit of a pause. But the pause might have been just from... it could have just been from the output, right? From console logging. And if I do time... Okay, so it's already 0.3 seconds. That's just calculating just one step per iteration. Because I figured I could pre-calculate them and then use them as a kind of lookup table. And I'm wondering, is there something I'm missing, or is it really that the iterations explode that fast? So we have nine places where we can put the first digit. Then we have 8 places. Yeah, it's multiplicative. It's not additive. I'm an idiot. Yeah. Okay, so this is not great. I'll be honest. I was hoping for not this. Is there anything obviously busted here? I mean, it might be a bit slow because I'm kind of doing some array stuff here, which might be relatively slow. Yeah, I don't know why I'm doing this. There's no point. Does if vowels.length is 0, if vowels.length is 0, can we do 0? I don't know. It might break. It returns what exactly? It returns an array with an empty array in it. So, what is vowels in that case? It's an empty array. If we do this, if we return an empty array... wait, this was already happening, wasn't it? And if we do 1, it does that. And if we do 2, it does that. Okay, so no, it already works for empty stuff. Right? All right, so that already works correctly. So it even works for Because this will be an array with an empty area in it. Ah, wait. Is that what we want? No, we don't want that actually. So if it's 0, 0, turn this. So that gets us an array with 1 element. This should give us an empty array. So no iterations with 0 element. 1 iteration with 1 element. And 2 iterations with 2. And then 6 iterations with 3. All right. And then if we go up to 9, we get that many. And if we look at the first one and the last one, it should give us 0, 1, 2, 3, 4, 5, 6, 7, 8, and 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so it definitely works. Yeah, that's column within each box grouping, local band. That's basically each group that's within the boxes, right? Oh, 80. I'm an idiot. I thought you said 81, not 81 factorial. The question is, yeah, this probably is expensive. The problem is here I'm just pre-calculating this. Now this I'm just going to do once, and this is just going to be a mapping for the number of options, so we can then iterate over these options. But it still means we need to iterate over those options, right? So well, let's put these in here. So we'll say let's call them opts 9 equals called options 9, right? And then we won't run through all of them. But basically we want to be able to apply it, right? So if we apply an option set to the list of 81 digits, we need a symbol mapping. I'm just trying to think. Where this should be the basic option, right? So this should be the default one. Yeah, I get it. Well, let's do our first iteration function, right? Const permute digits, and we'll get passed in a P81. I tend to call them S81 when they're a solution, i.e. when they're fully filled in. Let's do that. Let's just call P81 for simplicity. So we'll do that, and we'll probably want to do that. Oh yeah, we don't even need that. We'll pass the permutation in. So we'll do something like this. We'll pass in pos1. Let's put that in here locally. And we'll pass in ops9 0. Right? Let's see what that gets us. Okay, so it'll give us that permutation. Now, what we don't know is what I'm not sure is should this refer to the actual digits in these locations, or should it refer to the digits as they are currently in the puzzle? Do we care what the current setup is of the puzzle, right? Like if the puzzle already has a 1. So in other words, what are the 10 symbols? Are they the 9 symbols? Are they just the first 9 digits, right? Because then we'll basically get a straight up transform function that takes this and says, okay, every digit that matches the first digit needs to now to be whatever digit is in the nth place or something, right? So every digit, so if we go through the permutation, every nth digit becomes this digit, which happens to be the same one. So that's the identity, right? So we'll basically do something like this. And maybe we'll go with the last one instead. We'll do ops.length ops9.length minus 1. Right? And then we'll replace this one with the 8th, etc. Right? So let's go through this and see. Let's just actually let's do both, right? We'll do the first one and the final one. And we'll go through the permutation for let p of perm, right? So we'll have p, and the p is currently a digit, and that's gonna get us that character from the p81, right? So it's gonna be p81 p, and that's gonna be the character we're gonna replace. And what are we gonna replace it with? We're gonna replace it with the character in this position. Okay, so we actually want to do for let I equals 0, I smaller than. We actually want to do this. So we have I, and then pi, and then we have p81i and p81pi. I. Right? Oh man, I feel like such a noob. Let I blah blah blah. Let p equals perm I. So we have I, p, and that, right? So we are now saying the ith digit is 0, or I is 0 and p is 0. The ith digit is 1 and the pth digit is 1. Okay. The 0th digit is, so the ith digit is I0, the ith digit is a 1, but the 8th digit is a 9, which is this one. So it means replace all the 1s with 9s, replace all the 4s with 3s, etc., right? And we're gonna do that. So I'm trying to think what's easier if we just go if we just go looping through the digits. So if we do console.log p81.map digit to digit. Is that going to get us an array? Can we map that? Nope. Can I do this? No. I'm going to do split.map. Right? And they're not really digits. They're symbols in this case. And we'll join them back together. Right. So instead of doing this, we're going to do that in here. So we now want to map the digit at position n. Or let's call it the symbol at, no, let's call it D for digit at n. Right? Except we don't care about the current position. We want to map it back to whatever happens in row 1. No, yeah, that's what I'm saying. Like, I'm just going from 0 to 81, so I'm only changing each one once, right? So for each of these, we want to replace, if it's a 1, The problem is we actually need to figure out which of the 9 digits it maps, right? So we'll basically have to create a, we want to create a little lookup table. So we want to turn this into a lookup table. That's what I'm kind of, so we want to create a LUT, right? And we're going to do LUT, the symbol is this one, and it's going to become this one, right? So we do this, all the ones become 9s, all the 2s become 5s. All the 2s become 5s, all the 9 becomes 1. 5s become 2s, 4 becomes 3. Wait a second. This is right. So all 2s. So where do we have a 2? We have a 2. All the 2s become 5s, all the 3s become 4s. Yeah, okay, alright. So now we'll just do this, and we'll just look them up in the LUT. Like that. Right? So on the first one, it should become a no-op. And if we don't output this, it should be easier to see. So these are the same as these, and these should be the reverse of these. And we can test this out. Right? We compare this to this one. So wherever there's 1s here, we should have 9s here. And that looks like the same pattern. And wherever there are 1s here, there are 9s here, and 4s and 3s. So these patterns should always be the same. Okay, so that seems to work fine. And that should be fairly performant. Don't really need that. Right? Do that. And then we'll just return that. Now, do I want to deal with arrays, or do you want to go back and forth between strings and arrays? I think I'll probably want to deal with arrays only. So we'll get rid of this and this. And then here, we're going to split. We'll do a split here. And see what that does. And then here, we'll just join them back. Boom, right. Now, I'm kind of curious to see how long it would take to generate the 320 whatever thousand options. But I'm actually more concerned about memory usage. So we kind of have a problem. Like, I cannot really generate all the options because this gets multiplied up, right? So it's not 400, it's these many, right? So if they get all multiplied together, I need a way of pruning this so I don't have to generate them all, then sort them, right? And I think there's some stuff, like if you compare them as a number, it's like what you said. We actually, we make the first box 1, 2, 3, 4, 5, 6, 7, 8, 9, right? The problem is, I don't know how we do that. Like, from the digit swapping, I can do the first 3 digits. Well, I can do it with the digit swapping, right? But then the rows and columns swapping, like if we want to swap the first 3 rows and the first 3 columns, that would affect the first box. Does that mean we never touch these again? Like, we don't swap these, we don't swap these. So we'll make these 1, 2, 3, 4, 5 with the digit swap. So we don't actually need to do all of them. We'll just do that once. And then we only do row and column swapping on these and these. And we kind of keep these blocks locked. I'm guessing that's how it works. It for some reason, my brain keeps saying it feels like solving a Rubik's Cube for some reason. And maybe it is. Maybe it is. Maybe it isn't. So if we wanted to do that, we don't want to search through all of these, right? We kind of... It becomes a lot easier. We don't actually want all the permutations, right? We'll just want to figure out the right swap order. So what if we say normalize digits instead? Right? And then we don't need to do any of this stuff. We don't need to do any of this stuff. Because we only care about one of the digit swaps. Excuse me, my throat is still a little ticklish. So if we do this, and then all we want to do is we'll find the position of the one in the first box. So I kind of want to. I have tools for mapping things, mapping positions, right? So let's pull these out so we're not reinventing the wheel here. So I think this one does, or is it under? Puzzle tools. It's probably under puzzle tools, I imagine. So we do index to region, I think. So if we ask for a index to region by a row, by box, index, one sec, my brain. Puzzle tools dot index to region dot box. If I do this, 0, 0, 1 is 0, 3, that's 1. Okay, so it takes a puzzle index and returns the box it is in. So we want the opposite. We want region to index. So region to index. And then it's also the same, right? So if I say box, and then I'll say 0, and then I'll say 1. So, so it gives me now, it says, okay, what the first digit of the box is that? Because basically I want these 9 cells, right? I think I have a function for that as well. Get classic scene cells. Index to scene. If I do index to scene, I think that already does that calculation for me, right? So if I say for the box 1, why is this 1 based? Why is this instead of 0 based? So per box, okay. So the cell in this index gives me okay. It basically calculates which box cells are seen by a digit in this position. So this digit sees all these digits. So if I just do this, it'll get me that. All right, I'm gonna copy these over because they're super useful. I'm just gonna copy these over as helpers up here somewhere. And do that. I'm gonna get rid of that, that, and we'll do const these. I think that'll work. Right? And then we should be able to do this. PT. Okay. Yeah. So that so that gets us the indexes of the first box. And now we're gonna do what we said. So we want to have the ones in 0. But to get the ones in 0, we need to know where the ones are. We need to figure out what we need to swap it with, right? So first of all, we want to get these box. Let's see, right? I'm gonna output these, and then we'll do scene.map idx to e81 dx. So that should give us the index, the digits 145.268.739, right? And now we build our lookup table from these. Right? So we'll do something similar to here. But this time, what's this noise? What is this noise? So now we want to map let me think. So we have an index. We have the element. And we have it's annoying because the 1 is in the first position. Let's go with the second position, right? So we're in the second position. We have a 4. That means we want to swap the 4 with the 2. Right. So we want to swap this with this, basically. Well, the 4 has to be swapped with a 2. 1 gets swapped with a 1. 4 gets swapped with a 2. 2 gets swapped with a 10. No. Yeah, not IDX, but I. Right. Yeah, so 3 gets swapped with an 8. And 9 gets swapped with a 9. Okay, so then let this becomes this. I think. And we'll, yeah. Or we'll just do this. So we'll just say let p81, the IDX is scene I, becomes that. And then we output the LUT. Right? And now we can apply the LUT and we can return it. Boom. And then here we can join it back together. Right? And if we output the puzzle itself first, we'll get that. And if we test it like that, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9. And now, okay, so now we're basically skipping those 300 whatever transformations, right? Although I don't understand why you would want to do it on this rather than, if we're trying to minimize this, surely the first row would have to be 1, 2, 3, 4, 5, 6, 7, 8, 9, not the first box. Not quite sure why you said the box would be organized like that. Wouldn't you want to match it on the rows? Or were you proposing that the sort of puzzle value is calculated box by box rather than row by row? Because clearly this is going to be larger than something that has a 4 in this position. So actually, I think we don't want to do it like this. I think we want to normalize it as if it's a long integer already. And then we can just ignore the first row. And then we basically minimize by the remaining aspects of the puzzle. Or is it because we're doing some other transforms and it'll be problematic to not touch the first row? Or are we calculating the puzzle value box by box? You know, so it's like, these are the first 9 digits. Then we have these 9 digits, yada, yada. Because if we don't want to change this, we basically can't do any of the column swaps. And anything that's not 1, 2, 3, 4, 5, 6, 7, 8, 9 in the first row is always going to be a larger value. It feels like that's a must. So that's my instinct right now. Let me try that. Because then we're already taking a huge, like, these are the largest digits of our, 81-digit number. And we're already, by sorting these... Oh, wait. No, because we can never have 2 1s in this row, right? We can never have 2 1s in this row. So it's gotta be in increasing values. So the smallest puzzles would be 1, 2, 3, like overall. Then it would be 4, 5, 6 here. And then 1, 2, so it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6. 1, 2, 3, 7, 8, 9. 7, 8, 9. 7, 1, 2, 3, 4, 5, 6, right? That would be the smallest overall puzzle. I'm not sure if we need to pin the first box or the first row. Maybe it doesn't matter. Maybe we're not looking to minimize... Well, we are looking to minimize the number, aren't we? Because right now, we're not comparing different puzzles. We're comparing a puzzle to its own variations, right? And if I do this, there's always going to be another variation where this is a 4 instead of a 5, and it's always going to be smaller than this. So this cannot possibly be the smallest one. One is always redundant because the remaining 8 digits can be used to infer the 9th. Yeah, that's what I'm thinking. It's just because Jean-Paul earlier mentioned the first box would always be 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't see that must be true. Although, I guess if we swap these 3 with these 3, we still could get the 4 here, but we couldn't get the 5 here then. So we could get the 4 in here, but then it'll be 4, 8, 9, which is smaller than 5, 6, 7. So let's do this, right? And then that should normalize for the first row instead of the first box. So now this is one, so this is, the first row is now the smallest. And we can basically, from now on, ignore it. And now basically, without being able to swap these 3, and without being able to swap digits, we want to minimize the rest of the puzzle. I'm guessing that's the next step, right? Sure. So, but now we couldn't do any column swaps, so that's really annoying. Because that would prevent all, like this approach prevents all column swaps, because then it'll immediately make the puzzle larger again. I feel like I'm missing something. I'm not understanding something fundamental here. Hey, Ichtius, thanks for saying that. I appreciate it. Sorry, today's a bit of a weird one because it's technical mathematical, but I also don't know much about this. And I know that the Theory and Programming channel has dealt with this many times in the past. But I also don't know if this is actually, because whenever I asked, nobody had an algorithm handy. So I don't know if this is actually a solved problem, unfortunately. So starting from here, not being able to do any column swaps means this is always going to be a 7. Is that okay? I suppose. I suppose. So, and since we cannot swap these groups at all anymore, the only things we can do is handle rows, right? So basically, we want to minimize this digit. In fact, we can't... Well, actually, we could swap this one for this one. We could get a 6 here. That's the smallest digit we could get here. So maybe the other method is actually better because you have more tools available afterwards. Because there's no box swapping, so you're not blocking yourself there. Because you can still, swap all sorts of... All right, let's try that. Let's start from here and continue from there and see what would be the next step, right? And I don't know if there's my instinct says the next step would be to sorry. I'm just thinking rotation should happen earlier. But because once we are here, the 1 being in the upper left corner means that any rotation is always going to make the puzzle bigger. And maybe rotations and flips don't actually apply because they can be replaced by the other operations. And maybe I shouldn't do the digit swap first, but I should do the other stuff first and then do the digit swap last. Do the final minification? I don't know. You can do column swaps, then do row swaps as long as you undo the column swaps you did after. Not sure what that means. What I'm not sure is like what I'm looking to minimize next, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 on the first square, and I don't need to worry about all these iterations, right? We only did 1 digit swap. Now, what do I do next? Do I want to minimize this? Because if I move these over here, I get the 4 here. And if I probably need to compare these 3 with these 3 and these 3 with these 3, right? Although it feels like only the first digit matters. Like 5, 6, 7 is never going to be smaller than 4, 8, 9. And I can never get the 4 mixed in with these 3 either. And I guess that's where rotation comes in. Maybe there's another rotation. So maybe the digit swap isn't the first step, but the last? Because there could be another rotation where this ordering is easier to do. Or is more... I mean, here we're very close to having the perfect ordering just by ordering this, but that's coincidental. I can't count on that. What if we, instead of doing digit swap first, what if we develop some of the other algorithms, right? So, for example, we could do the column group swaps. We want to look at the lowest... Like, we can... Okay, so this is sorted. This should become 6, 7, 8, and this should become 2, 3, 9. Then we compare the first digits. Those should be 1, 2, 6. So these should go here. So maybe that's how we approach the rows and columns. The problem is I don't know exactly how to think about the rotations yet. Or is it that I have to do all these calculations, create all these groups, and then compare them by rotations and flips and all that stuff? Like, I can't mathematically generate the best option. I have to actually create different versions. And what I'm doing is like, oh, I just want to do 300,000 different options, right? So I guess what we could do is we could develop an algorithm which might not be perfect, and then say, okay, we apply that algorithm to each rotation and to each flip, and then we'll do the sorting. All right. Well, we've got an algorithm for the digit swaps. So let's just develop one of the other algorithms, right? So for example, let's compare this, I guess, the just purely smallest value in each column or row group, right? So we'll have a function called normalize call groups. And later on, like the row and column stuff, we can probably conflate. We can probably make them a single algorithm and then just have different mappings. So if we do this, right? This. Right? So we want to look at the first row, I guess. Because we can swap these. If we haven't done the digit swap yet, we could swap these, right? We could bring the 1 to the top. But there can only be 1. So we want to look at the 1s, right? So maybe that's how we do it, right? We look at the 1s, and then find the 1 with the smallest numbers near it. So it would be this one. So this one we want to bring here. Or actually, we do all the different... yeah, now I'm realizing, okay, yes, but this going here now depends on these as well. 5, 6, 8, and 3, 7, 9. While this going there now has 2 here and 3 here. So 1, 2, 3. This one would be 1, 3, 5. And this one would be 1, 2, 6. So I guess those are the iterations we want to look at. And that's for this row being at the top. So that would be our iteration calculation for that. Yeah. So we want to look... Because I'm trying to think, is it easier for me to find the ones and then calculate the smallest iteration and then bring that forward? Or just iterate through them all and find the smallest one of this subgroup of iterations? Because a simple algorithm that does more work sometimes can be faster than a slightly more complex algorithm that does slightly less work. Especially if it does, you know, if the work to make it more like as a human I can look at this, right? But scanning for the one might just be as much work as just going through the iterations, right? So if we want to look, so all right, normalizing column groups, we're just looking at the first 3 rows basically. And we want to look at we want to sort each individual one. We'll try that. Then we'll swap them. So we want to go through the 3 different iterations. Right. So we have our opts. We have our opts 9, which we don't necessarily want to use. But we have our opts 3. And our opts 3 is basically the different ways that we can organize the first 3 rows. Right. So, so for let perm off 3, that would be our each of the permutations, right? And each permutation value would grab a different row. And for and those come from this. So let's try this out. Index to scene row 0. So that would give us the cells of each row. Sorry, the cells of all the cells seen by the digit in. I just close it. 0, 1, 2, 3, 4, 5. No, we want 9 and 18. And I think instead of using index to scene, if we use region to region the index. Who is this? Right, that'll give us the indexes. Yeah, that'll give us the indexes of the 3 rows. So for each of these permutations, so if I do slice 0, 1, we're just looking at 2 permutations, right? Right. And each of these so we'll do for the let row IDX of perm. That gets us the index. Or the index, yeah. So 0, 1, 2 and 0, 2, 1. And if we do this, that'll give us the actual cell indices. And then if we map these to P81 IDX, and then we'll join them back together, right? So the first iteration should be just these two rows, start ending in a 9 and a 7, 4. And the second one would be swapping the bottom two. Right. And if I go through all of them, we'll get 6 different versions, where the final version is the inversion. Bottom row first. Okay, so that gets us all the different ways of arranging the first 3 rows. Now for each of those, we want to swap the groups, right? And we want to first sort each of the groups, and then we want to sort the groups amongst themselves, right? So that's the other we want to do for each of these. So 1 second. These are all the permutations. Now, if we're just looking at the first one, right, which is the identity. Now we want to sort the columns within each group, and then afterwards we want to sort the groups. All right, so we basically want to do sort. We don't want to sort the column groups. We want to sort calls in groups. And I guess we can build that, we can develop that separately to this one. Like it's a low level, it's a more primitive, or it's something that will be used by this one. I just hope I don't have to generate like a bunch of grids. If I have to do that, we're gonna run into problems again. Right? So now, now we want to look at the cells in Jesus Christ. We don't want to just we want to look at the groups individually. So we want to look at the first 3 cells of each of the boxes, right? So 0, 1, 2, 3, 4, 5, yada yada yada. All right. So for that box equals 0, box less than 3, box plus plus. Let's just call it B. So if we do this, it should give us these for the 3 boxes, but we only care about the first 3 indices, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? And then we want to map those to the puzzle digits, and then we want to sort those. And we need a helper tool that takes one of these sortings, maps it to the original one, and does the permutation thing. And I'm starting to wonder if I need to have like higher level helpers, like classes for rows and columns and boxes and things like that. So I can do these swaps in a more memory and speed efficient manner rather than like literally generating arrays and filling arrays with data over and over and over, because that's not going to be very performant, right? So this is going to be a little tricky. So, okay. I'm also starting to wonder if I want a helper to do this bit. Although now that I'm looking at it, I guess it's not too hard. So if I do this, right, so it'll get me the 1, 4, 5, 6, 8, 7, 2, 3, 9, right? So now I need to sort these. And I want an algorithm that lets me sort numbers and gives me the like a lookup table for the mapping afterwards, right? Because this gives me a sorting of indexes, right? So let's do this. Const sort in right? And I'll just take a list of values, and it'll sort the values, but it doesn't just give me the sorted list. It gives me a lookup table for the rearrangement, right? So let's do that. Sort lut vals. Let's top row. We'll do that. So 0, 1, 2, blah blah blah. Right. We want this, and then we want sort lut. If I do this, we want to sort this, but we don't want to return the values. We want to return the lookup table, right? And will the sort function do that for us? I mean, I guess we could sort them and then just afterwards find the relevant indexes, right? Because they're always going to be different values. So if we do just that, right? And then we'll convert that to a LUT. For let of group. We do this, or let I 0 sorted length I smaller than len. Right? So these are already sorted. So we get 0, 1, 2, 6, 7, 8. And we want vals.index of sorted I. Right? So 6, 7, 8. I think sorts vals in place, doesn't it? God damn it. All right. So we got to do that. So now our lookup table is element 0 becomes 0, element 1 becomes element 2, and element 2 becomes element 1. My god, this is a terrible puzzle to do this with. So we basically, or does it the other way around? I guess it doesn't matter. The first element becomes the second. Or sorry, the second becomes the third, and the third becomes the first. Because they're... one sec. I do this. It will give me something else, right? 268, 593, 359. So the first element becomes the second element becomes the first. The third element becomes... Yeah, it doesn't even... I think it doesn't matter. So we'll just say let lut equals that. Right, and then lut sorted I. No, lut I becomes this. All right, return the lookup table. Now, the lookup table is by index position, right? It doesn't care about the values. If I do this, 9, 10, 11, 2, 6, 8, and the lookup table would be 0, 1, 2. Yeah, okay, 5, 3. Yeah, so 0 becomes 2. Yeah. So we should be able to apply the LUT. Now, the question is, we need to do that with like rows and columns and all sorts of things, right? So let's go back to the first row. And now this will be modifying what exactly? Columns, right? This is just within the column groups. So so we kind of sort calls in groups. Okay, this is exactly what we want to do. Sort calls in groups. So for each of these, we want to apply this. And it's got... I'm annoyed that I chose columns first, because rows is probably a lot easier. But ultimately, it shouldn't matter. By using these... the iteration tools, I always just get an array of indices, right? I just hope it's performing in the end. Probably I can cache all of these. Like, these should all be cached, right? So I don't want to instantiate. I don't want to be instantiating arrays, right? All right. So, and I started late, so I'm not expecting to kind of conclude this in any satisfying way. Just learning how it works in general, get my head around it, get more familiar with the territory. Ah, my brain. Okay, so we now want to sort the columns in these. So let's just look at, so we want to do this. So the top row indices, we don't want to look at those. So then these are the values, 1, 4, 5, 6, 8, 7, 2, 3, 9, right? And then we want to sort columns in a particular box. Now, do we want to have this as a helper function? Because that's what I'm thinking, right? Like, well, I guess we can create a specific swap function, right? The thing is, I don't actually just want to swap. I want to actually kind of I'm trying to think what I want to do. Because you don't always want to swap. You want to apply, right? Because you probably need more swaps, potentially more swaps than just writing 3 columns, right? So I kind of want to rewrite three of these columns. So let's do this for a sec, right? So 6, 8, 7, and now we want to rearrange these columns, and we can create. We can find. We can find the cells, the indices of a specific column by region to scene. If I do region to scene column, and let's say column 3, which is 0, 1, 2, 3, which should be this one, right? So it should get us 3, 12, 21, 30, yada, 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 right? And then if we do the map to this, right? So that should get us 651, 732, and 894. So that gets us this column in index form, which means we should be able to take 2 sets of indices and just flip them, right? We have a from index set and a to index set, and those are given to us by these. So we go through these, and if they're different, so let's see, let's sort it lut equals this. Right. And then we'll go to through each of these for const whatever, a, b, from to of object dot trees. And I might get rid of that later. And we'll have from to. So it goes 0, 0, 1, 2, 2, 1, right? And we'll say if from equals 2, problem is, maybe we can do this. Continue. I don't like doing that. Yeah. So 1 becomes 2, 2 becomes 1. Yeah, and we ideally don't want to look into the existing one, right? And now we can look at this. Oh, hey guys, hey Toby. Yeah. Well, we have the. Right, sorry guys. Toby's home, so I'm gonna have to wind down soon. All right, I'd like to implement this because it's kind of a proof of concept. Because if we can do this, we can probably do all the other ones, right? So let's do something like this, and we want to do. Now the column would be, because we're in box B. Blip, 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 blip. 1 sec. Let's forget 2 for a sec. So we have B and from, because it's relative to being in the middle arena, right? And the B is 1. So if we take B times 3, right? So it'll be 0 here, 3 here, and 6 here. And we're adding from 0, 1, 2. So that should give us, but frickin', I need to normalize this stuff. Okay. It gets us 4 and 5. So column 4. Sorry, column 4 and column 5. Or the 2 froms. And the 2 twos will be the other ones. Right. Right. If I do this, and I can do this, from equals this, and 2 equals this. So now we should have converted this to real column numbers. Now we should be able to do this. And do the same thing for the 2 column. And here I'm converting it to the values, but because we have it all in indices, we can easily write it into the array. Let's just do this. So all these digits become these digits, so that's this one and this one, right? And now we want to let res equals actually we'll do right like that, but now we'll go let's see, let from id this and 2. And now if I output these, we should get two arrays with indices that we can now use to write in the values. Why is 2 indices different? Because I didn't update that. Right. And now I can just say res, for let was 0I smaller than. From idx.length smaller than len plus, and then we'll do res from idx I equals to idx I. And we do the wait, that's 2. That's from comes from here. Right? Now the output is this, and if I look at that, like in the same size, yeah. So the 5th and the 6th columns have been successfully swapped. So now this is organized 6, 7, 8. So now we can basically do the same thing for the others, simply by removing all the limits that we've put in. So if we go back to 3, although the other two are already sorted here, unfortunately, which is so annoying. Yeah, that's exactly the same. And now each of these column groups are sorted. And now what we do is we sort them by their values, which I believe only the first digit matters because, yeah, lacing, right? So the 2 will go here, the 1 goes here, and the 6 goes here. And then we kind of do the same thing again on the rows and columns. Or at least what I'm trying to get is, instead of calculating thousands and thousands of options, at the bottom of the tree, I want to get like, okay, this is the best option according to this, right? So this is the best option right now without arranging the boxes, right? So this is the best option for the first row, sorting the columns. Now we can sort the rows. We don't really have to look at anything else. And that's for the first row. Now we try this for the 6 options for the first 3 rows. And that should get us the overall best for this arrangement in the first 3 rows, right? So it should actually, I'm guessing this should go here. So it should be, my suspicion is it's going to be 1, 2, 4, these 3 digits sorted. Then the next one is 3, 7, 9, and then 5, 6, 8. Because you can't beat 1 and 2 in the first 2 positions, right? Like 1, 4 is bigger, 1, 4 is bigger, right? And that's how we kind of minimize the first 3. And once we've done that, we basically do the same thing on the columns, rows, and blah, blah, blah. And we might have to reuse that algorithm with other 3 columns in the first 3, right? We might have to do the same thing for these 3 and for these 3, and then some of these might go to the top, right? But that actually will happen via the doing the same thing on the first column, I think. All right, I think I'm going to call it here. But yeah, it's a step in this direction. I'm a little concerned because it's not the sort of thing I personally like to do, because other people have, smarter people than me have spent years thinking about this stuff already. And my concern is that this always seems to be an unsolved problem, which means I don't have a hope of solving it in a reasonable time frame, right? Like I'm not interested in this as an intellectual exercise. I actually just need it. But on the other hand, I don't actually need the mathematically correct version. I just need any improvement on just not doing anything is an improvement, right? So my algorithm will just go ahead, and whatever normalization I can do will improve the algorithm, right? Will reduce options for, basically one of the concerns is plagiarism, right? And so somebody could permutate a puzzle grid to pretend it's a new grid, and we want to detect that, right? And by normalizing the puzzles, we should be able to do that. All right. I'm gonna play today's gas puzzle just because I used to do that a lot. And today was a very dry stream, I think. So let's play some puzzles. That's what we're here for after all. Oh, well, what is this? That's unusual for gas. Big, small, odd, even by Clover. All right, what's she up to? It's an 8 by 8. Two sides of the grid stand for big, small, odd, and even. Okay. And describe the first 2 digits of that row and column. Close to the clue, for example. Okay, so we have 2 odds here. So that'll be 5 and 7, right? And they're resolved. And then we'll have the 6 and 8 over here, which are also resolved. We have 2 evens here, which are 2 and 4. And then 1 and 3, which are resolved. Okay. So the first 2 are big, which aren't 5. All right. And no, first 2 here are small. Okay, nope. Wait, why not 2? Okay, no, I see, because there's a 2 here and here. So 5, 7, oop, and 6 and 4, and even 2 and 8, oop, which results sort of, and 1 and 3. Okay, even. Right, now it's getting less obvious. It's only the first 2 digits, right? Yeah, first 2. All right. 1, 2, 3, 4, 5, 6, 7, 8. Right. And then these are even. Can't be a 6. So 2, 4, 8. Still can't be 2s. And that resolves these guys. 8 here. These 2 are even. 2, 4, 6, 8. And, oh, that's a 4. And the 6 are an 8. And I think that's it for the clues, right? Yeah, I think that's it for the clues. So 3, 4, 5, 6, 7. Oop. And here we are at 5 and 6, and here we are at 1 and 6. Resolved. 2, 3, 5, 7. 3, 7. All right, and here we are at 2, 7, 8. 2, 7, 8. Okay. What we got here? 1 and 3. They're resolved. We'll probably do a bunch for us here. 1. Yeah, I think that's it. That's it. That's the back of it broken. 5, 4, 8, 2, and 3. There we go. Nice and easy. Just the way I like it. All right. I'm gonna call it a day here. Bit all over the place. Got a late start. Need to get myself better organized. That's it. Thanks for hanging out, guys. Catch you guys in the next one. Take care. Bye-bye.